Good morning, everybody. Welcome to MAPRG. Oh, I have to mute here. Last day of this IETF meeting. Yeah, you made it until here. Hopefully you will enjoy the session. My name is Mia Kühlewind, and I'm very excited to have my co-chair in person next to me, Dave Plonker. So that's the happy note. The sad note is we only have remote presentations today, just like to make you aware, but we have some really good presentations, so I'm still looking forward to the session, and we can also have discussions with remote participants, of course, online. Do you want to take over?
Yeah, good morning again. It's been 4 years since I've seen you in person, and I'm happy to be on the same time zone as the meeting for a change. Let's look at the agenda for today after we cover the initial things. The IRTF's intellectual property policy is similar to that for the IETF, meaning you should be disclosing IPR if there is some involved with your work. Details, the links are there. The session obviously is being recorded, both audio and visual, so be aware of that. And I think by this time in this day, you know that the colors of your lanyard indicate whether or not you want close-up photographs. We have a privacy and code of conduct for the IRTF and the IETF. So we typically do not have problems in this group, but if you have any, what's that? It's a joke. We typically do not have problems in any group.
Can you get closer to the mic, please?
The links to the privacy and code of conduct issues are here. Please take a look at those. There is an ombudsman team that you can contact, a person that can help you through this if you have an issue.
Yeah, I just wanted to add, so like, even if you don't notice any problems, of course, there might be problems we don't know about. So in generally, I think being very friendly and being aware that not everybody is on the, knows all the background, knows everybody and so on, really helps us to improve our work. So please do that.
Thanks, Miriam. So the goals of the IRTF are different than the IETF. We do not create standards here. We do publish some RFCs, but it's a research effort, so not a standards development organization. So a little more relaxed in some ways, and just know that they're a little bit different, and we have details linked in the slides here. Links to the important things having to do with the meeting. It's important that you find the MeetEcho link or scan the code from the tablet that we're passing around here. And when we're running the session, when you want to get in the queue to speak either remotely or locally, please use MeetEcho so we know who you are and it'll manage the queue order for us. So it's sufficient to do either the scanning the code there and having it on, like, for instance, on your phone, or using the full display in your computer. We have a mailing list that the link was there. If you want to do follow-on work with MAPRG, please go there. That's also where we do for our call for contributions, which is how we got the content for today. Some tips about what the buttons mean in MeetEcho here. And here's the agenda for today. So we're doing the overview right now. We've got, let's see, that's 6 presentations coming up, each of which are scheduled for 15 minutes maximum for the speaker to talk, which will take us to an hour and a half. So I'm happy to say, for a change, it's been some years, we have less content than time. So there should be an average of 5 minutes for question and comments for each of them. So I'm looking forward to participating and giving some feedback to these speakers today. I'm going to get right into it, and you can see the topics here. We're going to start off with Kevin Vermeulen with Internet Scale Reverse Traceroute. And Kevin, are you ready to go? If you can request to share your screen, because you're doing it by screen sharing, we can give you that control. Okay.
Can you hear me?
Yeah, we can hear you. I'm clicking grant screen and it's not getting there.
So I'm not hearing you very well.
I have to stop.
I think I did ask for, yeah, okay.
Yeah, you did. It was me. I'm a little rusty with this. I stopped sharing my slides and now your screen's being shared. So it should come up. Okay, we can see your screen now, so you can focus on just the application that you want to share. There you go.
Right.
You can see your slide now. All right, Kevin, you got up to 15 minutes. You can go.
Yeah, thanks. Okay, so yeah, until now, no one has been able to measure reverse path at scale, so all our analysis is only half of the story. In this talk, I will present internet-scale reverse trace route, the first system that allows you to see the other half, the routes used by hosts across the internet to reach you. This work has been published at IMC in 2022. So why was it not possible to measure reverse path at scale until today? Well, we had trace route that could only reveal forward path, or we had reverse trace route, but it had some limitations. It did not scale, was not open, had all the limitations that I'm going to detail later. So what happens when you want to troubleshoot path? Let us suppose that you want to debug a bad performance between a client and your server. So in this case, you control the server. To troubleshoot the problem, you can use trace route from your server to the client, which gives you the forward path between your server and the client. In this case, traceroute revealed that the forward path is not circuitous and that the reason of the bad performance is not on the forward path. And then the troubleshooting becomes hard because we have no way to debug what is happening on the reverse path. And if the problem is on the reverse path, traceroute is unlikely to give the relevant information. As we found in our paper that 47% of the paths are asymmetric at AS level and much more at router level. And of course, you do not just care about one client, you care about all your clients across the internet, in particular if you're a CDN with multiple sites. So an internet-scale reverse traceroute system would solve two key problems: know where things went wrong, to know which operators to contact, and do it at internet scale to be able to have information about a maximum number of clients. And it can also serve in any scenario when you need reverse path, not only troubleshootings. So I told you that reverse traceroute exists but is limited. So here are some more details about its limitations. So we'll call it RefTR 1.0 for the talk. So on accuracy, it sometimes returns incorrect path without warnings, what could not trust any measurement. On throughput, it could not measure many reverse paths per unit time because it required many probes. And as we'll see later, reverse traceroute sends packets to measure reverse path. So the fewer packets you send per reverse path, the more path you can measure in parallel. And you cannot just ramp up the probing rate at the packets sent by reverse traceroute are record route packets that are more subject to rate limiting. So we want to minimize the number of them that we send in the network. Finally, on coverage, it could only measure reverse path to Planet Lab and MLab sources and was not open to outside sources. So this means that an operator in the previous example could not measure reverse path to its own sources, limiting the usefulness of the system. So in this work, our contributions were RefTR 2.0, an internet-scale reverse traceroute system capable of measuring 50 million reverse paths per day with high accuracy from 40K ASs and allowing outside sources. This is way above what the original reverse traceroute was capable of doing, and this means that our new system can be an everyday part of the internet measurement toolkit of researchers and operators, or just like forward traceroutes are today. We also provide in our paper a demonstration of how to use RefTR 2.0 to troubleshoot poorly performing path with an example very similar to the one I presented at the beginning and a large-scale study of internet path symmetry. So I've shown why we need RefTR 2.0 and what are its high-level capabilities. So let us step now to a presentation of the key ideas to build RefTR 2.0. To be clear, the basic technique to measure reverse path is the same as RefTR 1.0, but we identified the key design question of a reverse traceroute system to overcome RefTR 1.0's limitations. And RefTR 2.0 is a culmination of insights found in our earlier work, as well as new measurement techniques and studies that we led in this paper. To understand the design question that I'm going to present, I have to introduce the basic techniques of RefTR 1.0. So recall that our problem is that we want to measure the path from destination D back to our source S. So in the example that I showed at the beginning, we are the operator of a server S, and we want to debug the performance of the client D. The first idea to find reverse hops is to build an atlas of path to S from vantage points that we control, here V1, V2, and V3. So if later we intersect a known traceroute path because of destination-based routing, we assume that the rest of our path is the same. This does not give us the full path from D, but it gives a baseline we can build off. The traceroute atlas gives us a good basis, but will typically not reveal hubs close to the destination. To reveal them, reverse traceroute uses the record route IP option. With the record route IP option, each router on the path that implements the option records its interface. Up to 9 interfaces can be written in the record route IP option header. In our example, if we send a record route packet from S to D, router on the forward path, F1 up to F4 will record their interface. Then, when D responds to S, reverse hops R1 up to R4 will fill the rest of the record route slots. So this is great if you're near enough to use record route. But in average, a path is more than 8 hops. So what if D is not within 8 record route hops from S? If S is not close to D, all the record route slots will be taken by the forward path, so we will uncover no reverse hops. To overcome this limitation, we try to find a vantage point close to D and spoof as S. So here, V2 sends a record route packet to D, spoofed as S, and when the packet arrives at D, as V2 is within 8 record route hops from D, similarly to what we've seen before, there are slots available for routers L1, R2, and R3 on the reverse path to put their IP address. So, and then we continue to send spoof record route until we intersect the trace route. Here we send the spoof record route from V1 to R3, revealing R4, R5, and R6. Finally, R6 intersects the trace route from V2. So we're done measuring the reverse path. So now that we've seen the basic RefTR 1.0 techniques to measure a reverse path, let me give you some of the design questions related to these techniques. First, for the traceroute atlas, when the number of sources and vantage points increase, we cannot issue from all vantage points to all sources, and our problem budget will be stretched even thinner if we need to keep the atlas up to date over time to avoid introducing errors. So we had to smartly select the traceroute that we issue, leading to a first design question: which traceroutes to issue for the atlas? Second, it is not easy to identify that R6 intersected a hop in the traceroute from V2, because traceroute and record route do not necessarily reveal the same interfaces of a router. So we have a second design question: how to identify intersections between record route and a traceroute atlas? And third, how do we choose the best vantage points for any probe to measure as many hops with as few measurements as possible when we have to spoof? I will only delve into details for the first question because of time constraint. More details can be found in the paper and the other ones. So let me dig now into that design question that I've presented in the previous slide. So the question was, which trace routes to issue for the atlas? So the challenge in that problem is that we are using RIPE Atlas to issue the trace routes, a platform that has a high number of vantage points, but it's rate limited. So the more hops we can measure with trace route, the fewer we have to measure with record route, which are, as we have told before, a limiting factor of throughput. The goals are to maximize the number of hops coming from trace routes to save record route probes. And we also want to minimize the number of stale trace routes in the atlas to keep a high accuracy. So I'm going to show the insight that we found, that a random selection of 1,000 trace routes per source suffices to get the most important hops. By important, I mean whether it is intersected by many reverse trace routes and whether it is many hops away from the source, as these two factors impact the number of record route probes that the hop will save. To demonstrate this insight, we run trace route from all the 10K RIPE Atlas probes to our sources. We use 5K for the trace route atlas and the 5 other K as reverse trace routes back to our sources to see where they intersect the atlas. On this graph, on the x-axis, we vary the number of trace routes per source in the atlas, while on the y-axis, you can see the mean fraction of hops in the reverse trace route coming from the atlas trace route. So the higher, the better. We can see that the random strategy is close to optimal, which we define with an oracle knowing in advance the reverse trace routes that will be issued. What we can see is that 1,000 trace routes gets us most of the benefit that we would get with 5,000 and is close to optimal. So let me tell you some other results that are not shown on this graph. Only 0.7% of reverse trace routes intersect a stale trace route if we keep trace route in the atlas for a day. So we can say trace routes are valid for a day, and therefore we do not have to reissue them during the day, saving a lot of trace route measurements. Finally, the atlas converged to optimal in 5 days, where during 1 day we run reverse trace routes, compute the intersection with the trace route atlas, and keep in the trace route atlas the trace routes containing the most important hops and replace the others with new random ones. So now that we've seen how we select the trace routes for the atlas, let's look at the impact on throughput. So we see that 56% of the hops of a RFTR 2.0 measurements actually comes from the trace route atlas on average, saving record route probes. Indeed, vantage points will send fewer record route probes per reverse path, letting them measure more paths in parallel. So now that I've shown some ideas behind the design of RefTR 2.0, and I recall the other ideas are available in the paper, let us step into the evaluation. So these are the results that I introduced at the beginning with some more details about RefTR 1.0. So we see that RefTR 2.0 has a way better throughput and a better accuracy than RefTR 1.0, and it allows outside sources. With this throughput and accuracy and the ability to measure to your own sources, RefTR 2.0 is ready to serve the needs of operators and researchers. Another result that is detailed in the paper is how RefTR 2.0 compares versus other approaches. To measure reverse path, you could, for instance, run trace routes from RIPE atlas to your sources or perform forward trace route and assume symmetry. In the paper, we show that RefTR 2.0 is an order of magnitude more complete than RIPE atlas. As with RIPE atlas, you're limited by the ASs with a probe in them, which represent about 4K ASs. We also show that RefTR 2.0 is also more accurate than assuming symmetry, as we found that 47% of their paths are asymmetric at AS level. So now that I've shown some results for RefTR 2.0, let me step to the use case on how one can use RefTR 2.0 to troubleshoot poorly performing path. To show how a CDN can use RefTR 2.0 to troubleshoot poorly performing path, we deployed RefTR 2.0 on the peering test, announcing an anycast prefix. After having announced the anycast prefix from peering sites, we measured the performance of clients that are represented by destinations representative of a CDN clients. So we measure the performance of the different clients, and we observe that some ASs located in the southeastern US, here I show least web and North Texas Gigapub, have bad performance because they are routed to the Brazil sites, whereas they should go to the closer site. Without reverse trace route, it's hard to say why. So to find the root cause of this problem, we run reverse trace routes from all the clients, finding that least web and North Texas Gigapub are some cogent clients. The response to improve the performance is to restrict the Brazil announcement to not propagate to cogent. And after that, we verify least web and North Gigapub are routed to Boston with a good performance, improving RTT by 70 milliseconds and 99 milliseconds. So these examples show three things. With RefTR 2.0, you can find which routing decisions made some clients end up at a suboptimal site. And you can do it for your own sources if you're an operator, as the system is open, as we'll see later. In our example, peering played the role of the operator. Then accuracy allows you to trust the results. And the coverage of RefTR 2.0 allows you to measure reverse path for many clients. And the throughput allows you to include reverse path measurements in reactive traffic engineering system. So to conclude the talk, what we've seen is this talk is that traceroute cannot give reverse path, but RefTR 2.0 can, and it can do it at scale, overcoming RefTR 1.0's limitations. RefTR 2.0 has already proved to be useful in other contexts. We used it for another IMC paper which looked at traffic engineering strategy during failover, and we were told that a security company was using our API to uncover the providers of malicious AESs. So finally, what I would like to tell is that the RefTR 2.0 is an open system. It is currently deployed in MLab. And if you want to run reverse trace routes, please ask for an API access to that email. And if you also want to run reverse trace route of your own source, it's possible to add your source in the system. And same process, you send an email to the given email there with the following information. Thanks a lot for your attention, and now I'm open to questions.
Thanks a lot, Kevin. Folks, please use the little hand icon in MeetEcho to join the queue. I see Tim's in there. We've got up to 5 minutes, and Corey's in there. So
should I look at the should I look at the chat now, or yeah?
You'll be able to hear them asking the questions
okay.
via audio.
Yeah, and I'm not sure if you're able to turn on your video, but if you would like to, it would be nice.
Sure. Yeah, I can do that.
Go ahead, Tim.
We can see him turning.
Yep, there he is.
Hi, Tim Chan. So my understanding is the record route option is a V4 thing. So what are you doing for V6 reverse routes?
No.
So if you have a solution, I'm very happy to to hear it, because yeah, as you said, like the record route option is only available in V4, so we have no solution currently for V6.
I will not mention hop by hop.
Sorry. We kicked you off the video, so you have to turn your video on back again.
Oh, sorry.
All right, Gory's up next.
Hi, Gory Fairhurst. That was a fun talk. I'm very fast, but I saw a lot of interesting stuff. The question I have is, what was the packet that you used when you did the record route? Because I do stuff on ECMP, and I see the transport payload makes a difference to the routes we see. So did you look at different packet types? Is it just an IP packet with no transport, or what is it?
It's ICMP echo request, actually.
So it's just the ICMP traffic. Yeah, okay.
Yeah, but you're right. Like with ECM, so what we observe is that when there are ECMP on the path, record route is treated like per packet in general.
Okay, I mean, that was a really great presentation, so it might be fun to look at that as well.
Thanks.
Thanks. Ben Schwartz is up next.
Hi, Ben Schwartz, Meta. So this is not the IETF, but we're very near to the IETF. And, oh, is this microphone not?
No, it's the video, so he can see you.
Oh, yeah.
Okay, hello.
Hey.
So we're very near to the IETF here, and the IETF is in the business of making changes to internet protocols. My understanding is that you chose not to make any changes to internet protocols here, but if you could, would you do this differently?
So yeah, so basically this, like, all this work looks like using some hacks to get the reverse path, right? So I know there is a reverse trace route RFC draft going on. I don't know the state of it. So my sense is that during the whole process, while this RFC might be adopted someday, we should use that system to get the reverse path and then shift to something that is less hacky, probably, to whenever the RFC gets adopted, if it gets adopted someday. But there is something out there, like a new. It's basically based on new IC. It's not from our group, but it's based on the new ICMP type or code. I cannot remember, but message that would trigger a reverse trace route. So,
okay, thank you.
Yeah. Thanks a lot, Kevin. Thanks for joining us. Oh, we've got Tim Chone in the queue. Let's take Tim's question or comment. No.
Hi, Tim Chone again. So, as Gory said, there are a lot of very interesting things now. I think you said right near the start that something like 60% of the reverse routes you looked at, well, the routes were asymmetric. Was that correct? Or was it 40?
I'd say it is 47% are symmetric at AS level. And that's many more,
okay.
Probably.
Okay. All right, thank you.
All right, thanks for joining us from far away, Kevin.
Thanks a lot.
Yep, take care. Okay, we have Jay Azri Sengupta up next. I'm going to share his slides. Jay Azri, can you say something? Hello. Jay, can you say something?
Hi, am I audible?
Okay, we heard something. Can you test again?
Yeah, am I audible now?
Yep. That's good. Anyway, your slides up and you're ready to go.
Yeah, thank you so much. Yeah. So good morning, everyone. So my today's talk is about web privacy by design. And this is part of a master's thesis done by Justus at Technical University of Munich. And the work is funded by Volkswagen Foundation. And it was published last month at IFIP Networking Conference. So we begin our today's talk. So as we know that so traditionally, unencrypted DNS over UDP is still used as a default for every DNS resolution on the web. As a result of which, what happens is that the third parties, they are able to create user profiles because they are always able to see what kind of DNS traffic is being transferred. Though these days browsers offer users to opt in to use DNS over HTTPS, but users have to specifically opt in to use it. And over that, the other problem is that both DOH and DOT, which are the encrypted DNS protocols that exist now, have several problems, like they are limited by head of the line blocking problem as well as the multiple round trips. So as a consequence of which QUIC was standardized, which eventually led to the development of DNS over QUIC, that is DOQ, which is the new player. And DOQ brings in the advantages of faster handshake, as well as it removes this multiple handshake problem as well by reusing the same by using HTTP3. And but however, we realize that even when using QUIC with DOQ and H3, improvements are pretty much uncoupled. And this figure actually shows the typical web browsing scenario that exists in today's world. So the question here is that how to improve the web browsing experience with inbuilt web privacy by design. And that is what we explore in today's talk. So the idea that we put forth in this work is to reuse the same underlying QUIC connection for the DNS resolution using DOQ, as well as the web content delivery using H3 with zero RTT. We basically coalesce both the connections to so that it happens over the same underlying zero RTT QUIC connection. And that is what we show in this figure as well. So that every fresh H3 request to the web server is also served using the same connection. And we believe that this will not only make the web communication private as well as faster, and it will offer more optimization potential. So the major question that comes from these proposal is that what is the impact of reusing the same QUIC connection on web performance, and how does it impact for both fixed and mobile access network technologies? And these are the two questions that we explore in the next few slides that are coming up. So here we present in this slide, we present our methodology, which is our measurement setup. So in our measurement setup, what it does is that our measurement setup automates the DNS resolution and the web browsing while emulating network conditions of a user at the edge. The setup is encapsulated in Linux network namespaces by enabling separating client and server into different network domains. And it primarily decouples the DNS resolution from the actual web page loading on the client side, whereas on the server side, we have the DNS server and the H3 server running under the same process as a design choice. And the Chromium browser is used to measure the page load times of 3 different categories of web pages. So we have a basic HTML page, another HTML with JavaScript asset, and the third page is HTML with JavaScripts and CSS and other cookies. So we perform the experiments under different network conditions, which are emulated using the NetTeam package. So we have the fiber, the cable, the DSL, and 4G as well as the 4G medium, and we use the FCC's measuring broadband dataset to represent the fixed broadband scenario, as well as the RNet dataset to represent the mobile wireless access technologies. So as part of the measurement, we have made certain changes to the open source tools such as the Core DNS and the Chromium, the details of which is available in the paper. And during the evaluation, the data points are either normalized by the scenario's delay or the round trip time of the access technologies, depending upon the need. So next, we move on to the evaluation. So our evaluation is broadly broken down into 3 stages. So we first evaluate how QUIC interacts with the different application layer protocols, that is DOQ and H3. We then move on to evaluate the DNS overheads, and finally we move on to the performance evaluation of how our emulated setup behaves under different network conditions. So in the first set of experiment, we see that H3, so we see the handshake connect durations, and we see that H3 1 RTT connect times roughly corresponds to the DOQ handshake times, where the difference between H3 0 RTT and 1 RTT is less than 1 round trip. And certain distinct step patterns are also visible, which refers to the different access technologies that we use in our measurement. So what we realize from this is that the performance of DOQ and H3 1 RTT are majorly synchronized, and in general metrics scale well with round trips. So in the next set of experiment, what we try to analyze is that how does QUIC scale while interacting with both DOQ and H3 under different network conditions. So here we show the plots for the fiber scenario as well as the 4G scenario. And from the fiber scenario, we observe that the connect times have a long left tail in the higher percentiles, and 1 RTT has a relatively large left tail from minimum until the 20th percentile. And since, as I already mentioned, that these are the scenarios delay, normalized by the scenarios delay, therefore we realize that the actual data for 0 RTT has less variations compared to that of 1 RTT. And when we compare the graph for the fiber scenario with that of the 4G scenario, we realize that the 4G handshake time scales better with RTT while having less variation. So as a result, the takeaway from this slide is that the processing delay is large for lower RTT access technology, while in absolute terms, the processing delay is same for higher RTT access technology. It weighs in much less relatively, resulting in the observed differences being small between H3 0 RTT and 1 RTT. So next we move on to what is the overhead of DOQ and DOH in comparison to DOUDP. So here we see that we can again see the steps that are visible, which is because of the different access technologies, as I already mentioned. But here we see that there are no steps for DOUDP. However, for DOQ and DOH, they do not exhibit the expected number of round trips as it should be. So the DNS exchange duration of DOQ is 1 round trip faster than that of DOH. So next, we again see this in comparison to different network conditions. So here we observe that there are left tails for lower percentiles visible for both DOQ and DOH, which eventually starts getting smaller for from fiber to 4G scenario. And the range of values for 4G is much smaller, implying that there is less variation in the data. So again, the takeaway is that the lower RTT access technologies exhibit longer left tails, which eventually get smaller with increasing delay. Now we move on to the actual evaluation, where we evaluate the impact of our emulated setup. So here we try to see that how our emulated DOQ with H30 RTT setup performs across different access technologies and web pages with respect to its competitors, that is with respect to its competitors, that is the original DOQ as well as the DOH. So here we see that along the x-axis, the web pages are placed according to their increasing level of complexity, whereas the access technologies and the y-axis are placed in increasing order of their delay. So from the graph, from the heat map, we see that DOH has the highest relative increase across all web pages and access technologies. And the example page shows the highest relative increase overall, whereas the relative increase for the Wikipedia page is greater than that of the Instagram page, with just one exception where we see it is being highlighted in the red box. That is the Fiverr scenario, where we see that the Wikipedia page performs better compared to the traditional DOUDP as well. And the other observation from this heat map is that the performance of the access technologies degrade in order of their respective round trip delays. However, there are quite a few exceptions to this. For example, we see for the example page in the DOQ setup, we see that the DSL performs worse compared to 4G or 4G medium. And even for the Instagram page in DOH, we see that Fiverr performs worse compared to DSL. So this heat map was actually showing us the median relative PLT increase. So on the next slide, we actually go in more detail, and we show the entire PLT increase, the entire, with not just the median values. So from here, we again have quite a similar observation that example page has a short left tail, and Wikipedia has a longer left tail, and Instagram has no left tail at all. And the difference in percentage points between the protocol combination is smallest for the Instagram, whereas it is largest for the Wikipedia. And difference between the protocols, that is DOQ and DOH, scales well with the round trip as expected. And difference between H30 RTT and 1 RTT does not scale with round trip as expected. So what we realize from this slide is that both dimensions have an effect on the relative increase over the baseline, and increasing delay between the client and the server reduces potential time savings of 0 RTT, while savings using DOQ instead of DOH increases. So in the end, we try to analyze the overall impact of DOQ with H30 RTT, that is our emulated setup, against the baseline, which is the typical web browsing scenario of using DOUDP. So here we see that, so here we do the emulation. Here we have 15 data points with one for each web page and access technology tuple. And here we see that DOQ with H30 RTT setup matches the baseline for one tuple, as we had already shown in the heat map, which where the median relative increase is around 7.3%, and median of DOQ setup is slightly higher at 10.8%, and DOH setup has an average relative increase of 14.7%. And the interesting fact from this slide is that even in the worst case scenario, DOQ with H30 RTT, that is our emulated setup, is at 26%, whereas DOQ is at 31% and DOH at 53.7%. Therefore, what we understand from the entire set of results is that using H3 with 1 RTT, PLT for DOH is inflated by greater than 30% for fixed line and by over 50% for mobile compared to unencrypted DOUDP. However, when we use our emulated DOQ with H30 RTT, it reduces the PLT by 1/3 over fixed line and by half over mobile compared to the existing setup. So we discussed the few limitations and the future scope of this work. So we see that our emulated setup decouples the DNS resolution from the actual web browsing process. So in the future, we want to actually make changes to the Chromium, which will support for DOQ to be incorporated, so that both of the DNS resolution and the web browsing is coupled together. And the measurement setup of also uses DOQ with H30 RTT, that is currently limited to web pages having a single DNS resolution, and it is also implemented with a single H3 server right now, which is uncommon, which is a pretty uncommon scenario if we consider a real life web page loading. And therefore, we also want to extend our methodology in the future to incorporate web pages with more than one DNS resolution, and also incorporate cross-traffic network conditions. And finally, as DOH3 is also coming up, we would also like to incorporate that in our measurement setup. So overall, the takeaway is that DOQ with H30 RTT performs best across all web page and access technology combinations, even in the worst case scenario, as we had seen, that it performs better compared to the other competing ones. And yeah, that we have already said that DOQ with H30 RTT reduces our page load time by 1/3 over fixed line and by half over mobile compared to the existing web browsing scenario. So our code is available in the GitHub repository. Yeah, the link of which is given. Thank you.
Thanks, Jayasri. That's right on time. So we've got plenty of time for questions and comments, and we have 3 people in the queue, and up first is Ben Schwartz.
Yeah.
Hi.
Hi.
So
again, maybe if you want to turn your video on, we would appreciate it.
Sorry. Yeah. Hi.
Hi. So first I wanted to say, as a matter of terminology, I think you're using DOQ in a way that doesn't quite match with the way that that term has been used at the IETF.
Yeah, you're right.
I had a little bit of difficulty understanding what protocols you're referring to in these different slides. I think, if I understand correctly, most of the time when you use DOQ here, I think you're referring to something that we've referred to as DNS over HTTP3, or if you need a short form, DO3, like you had in I think slide 12. Is that correct?
This one?
So
you're asking whether we are using DOH3?
So at the bottom, you have DO3 here, DO3 support in the last line.
Yeah.
Is that the same as what you mean by DOQ plus
No.
H3?
So what we are trying to say is that so what our measurement setup right now says is that we are trying to serve the DNS resolution as well as the H3 web content from the same server by putting both of them together under same process right now as per the measurement, so that when the web content is also being requested, it happens with the same underlying quick connection, and a new quick connection is not required. So currently this is the concept.
Okay, I believe that in that case, I still think that you're telling me that you're using DO3 for the DNS query. You're using DNS over HTTPS using HTTP3 over a quick connection that's also used for the web HTTP3. Okay, that is in IETF terminology not considered DNS over quick. DOQ is a separate technology in which the HTTP layer is omitted. So just as I would encourage you to just adjust the terminology that you're using to describe, because it's confusing for some of us to see these terms used in different ways.
Sure.
I think my fundamental question is, why would it ever be the case that the DNS server is co-located with the web content?
That is of course a very good question. So the idea is that so we thought of this in this way, that currently the content delivery networks, for example Cloudflare, they are also serving, so they have this web server as well as the H3 server. They are serving it from the same edge network. So it could be a possibility. So this is a proposal where we are looking into the future, that it could be a possibility that they serve both of it from the same server.
Okay, and if you get a response back that tells you an IP address that is not the same as that server, so I have a web connection open to some server, I get a response back, but if a DNS request was necessary, it's because I don't know the location of the content. If it comes back with a new IP address, surely I have to start over with a fresh connection, right?
Yes, definitely, yeah.
Okay. So there's a lot of people who want to talk here. I'll just mention that if you haven't run across the resolverless DNS topic, which has been discussed here and there at the IETF over the years, and also in other contexts, I would encourage you to look at that literature, which has explored this problem space a bit. I would also want to encourage you to take since you're in Chromium, I'd recommend looking a little bit deeper at why why the DO connection and the web connections are actually partitioned so that they cannot share the socket pool. And that is connected to things like client identifying authentication, which is important for the web content, but undesirable for the DNS requests.
Sure, I'll definitely look into it. Thanks.
Thanks, Ben. You cleared up a lot of things there. Next up, we have Mike.
Mike Bishop, Akamai. I think I came up with a lot of the same questions as to when this would actually be the case.
Yeah.
I had interpreted this as a hybrid protocol that could do DNS on some streams and H3 on others. So yes, please clarify exactly what the nature of the protocol is in.
Yeah, so as I already mentioned, as this figure also shows, that we are trying to coalesce the DNS resolver as well as the H3 server into one infrastructure on the server side, so that we can serve both the DNS resolution as well as the H3 by using the same underlying quick connection.
Right. So it's DNS on some streams and H3 on others?
Yeah.
Okay. And in this scenario, how did you come to connect to the server in the first place? Is it your configured DNS server? Is it a web server you already happen to be talking to?
So here we are just doing it inside our Linux network namespaces. So what we are doing is, so we have this core DNS tool, which is giving us the IP address, and then we are sharing the IP address with the Chromium browser, and then the Chromium makes the request to the H3 server. The only difference in the measurement setup is that for the time being, we have kept the core DNS as well as the H3 server under the same process on the server side, and that's why we are being able to reuse the same quick connection.
All right. So I understand for experiment setup, you're just feeding the IP address in, but the situation you're trying to simulate in the real world.
Yeah, so that's with the current. So
as
I already mentioned, that this is a futuristic thing that we are trying to look at, given that CDNs are already they have the servers, they have the server support from the same edge network. So maybe this kind of a coalescing would be possible with some infrastructural changes at their end.
Okay, thank you.
Thanks, Mike. Up next, we have Anthony Somerset. Cool, thanks. All right, Spencer Dawkins, are you still in the queue?
Spencer Dawkins, I apologize. I thought I had a moment to stall. So I wanted to thank you for working on IETF technologies that are still new enough that we keep changing the names.
Yeah.
And I really like where you're headed, and we are doing other protocols over quick that we have like media over quick and RDP over quick that we're going to have the same kind of questions about. And I think you have an opportunity to do a lot more research in this space that would be very valuable to us. Thank you.
Thank you so much.
Thanks. And we'll wrap up the queue with Eric.
Right, Eric Kinnear, Apple. Yeah, I would echo that. Thank you for the talk and doing some of this research. I think it's super interesting. One of the things that you mentioned around having the server do the thing, and to Mike and Ben's question, once upon a time, we did have a document that talked about the concept of kind of designating a resolver for a given domain or zone. And so even if I wouldn't necessarily want to have a generic resolver that I could talk to that would also accept HTTP requests for content, perhaps for someone else, saying if I am serving this content from this domain, I'm also would like, and I can prove that I'm authoritative there. I also would like to provide better DNS privacy potentially than you'd get from your local resolver on your local network. So some of that is a concept and is a thing. I think some of the questions around how do you partition and who knows what about whom are things that we'd want to probably answer.
Yeah, sure. We would definitely look into it. Yeah.
But thank you for bringing this here. This is really cool.
Yeah, thank you so much.
All right, thanks Jay Esri for bringing this measurement experiment to us.
Yeah, please check also the chat. There's more there. Yes, thank you.
More. So I've been trying to get in touch with Ali, who's up next. Ali, are you with us?
Hello, can you hear me?
Yeah. Well, let me get your slides up here. And...
Can you hear me?
Yep, we can hear you.
I cannot hear you. I don't know why.
We can hear you. We're getting your slides there.
Okay.
And now you should be ready to go.
And I just passed slide control to you, so you should have controls on your Meet Echo screen where you can advance the slides yourself. And Ali, can you tell us how to pronounce your name?
Yeah, can you hear us?
Hello.
Hello.
Okay.
Ali, can you hear us?
Yes.
Okay, you're ready to go.
Yeah, and should I share my screen or what?
I've shared your slides already. You should see them through Meet Echo, and you should have slide control on your screen. If you don't, I'll take control back and you just tell me when to advance the slides, but you should be able to see your initial screen right now.
Yeah, I can see my slide, but I cannot see my notes.
Okay.
No, you probably have to put your notes in a separate window then.
Okay.
Or if you'd rather share your screen, I can stop this and you can share it yourself.
Can I share my screen?
Yeah, so request to share. Oh, yeah, you do. Thank you. Okay, it's loading up.
Let me go to the presentation mode. Okay, now you can see my screen probably.
Yep, you're ready to go.
Okay. Hello and thanks to join my talk. In the following minutes, I'm going to present my recent study published in PAM 2023, which was done as a collaboration with my colleagues Shivani, Devashish, and Oliver. As the title implies, it's a privacy measurement study focusing on web cookies, in particular the role of cookie banners on today's web. Before we delve into the main contribution of the paper, let me first briefly introduce two types of web cookies. Technically, cookies are a small piece of information stored on a user browser by web servers using HTTP headers. Once set, the browser includes them in the subsequent request toward that particular domain. There are two types of cookies based on their origin. First-party cookies, which are those that are set by the website that the user is currently visiting, and the third-party cookies, which are sent and received by the domains other than the actual domains the user is visiting.
Sorry to interrupt you, but your audio quality isn't that great. I'm not sure if you can get closer to your mic or anything like that.
Okay. Maybe is it better now? Now it's better? Can you hear me?
Now it's better. Thank you.
Okay. So yeah, and as an intrinsic part of the web technologies, cookies offer valuable advantages like enhancing the intelligence and coherence of HTTP requests. For instance, they can be used in storing shopping carts and optimizing online advertisement. However, the extent of their usefulness depends on how cookie collectors actually do behind the hood. In particular, cookies can be employed to track users and gather information about their highly personal data, such as browsing behavior and history. These undoubtedly raise privacy concerns. To address these issues, regulators have established laws.
Sorry to
Yes.
interrupt again. Your audio is
No problem.
changing like between multiple modes. It's sometimes good and then we
okay.
can't understand it. So
Okay, let me just change my audio.
it sounds good right now. Whatever you're doing right now is good.
It's good now?
Yeah, we can hear you now.
Okay.
It
good.
just sometimes kind of overloads and we can't hear it. But it's good right now.
Okay. So where I was? Okay. Yeah. To address this issue, regulators put some laws and directives aimed to mitigate the potential privacy risks posed by cookies. One of the regulations that you probably heard about it is GDPR, enforceable since May 2018. It's a European Union regulation aimed to empower individuals by granting them greater control and rights over their personal data. To comply with the GDPR, websites operating within EU are required to obtain user consent for the collection and tracing of their data, except when such data are strictly necessary to provide the required services. Similarly, the CCPA is a state law in California that took effect in January 2020, faring similar as GDPR. The CCPA's aim is to safeguard the privacy of California residents. In response to this regulation, publishers have implemented cookie banners on their website, which serve as a simple method to compliance with it. As a result of these changes, several questions arise, such as how many of websites show the banner? Does the banner have the explicit accept and reject button? Do they really respect the user choices afterwards? And do websites behave differently with different users, for example, with regard to their geographical location or browsing user? A couple of recent studies try to answer some of these questions. However, most of them doesn't consider different aspects that impact the result. In addition, their measurements are conducted in a manual or semi-automated way, which makes it hard or impossible to reproduce the result for another time duration or configuration or for consistency analysis. And a study by McHugh, it all tries to tackle this problem. They introduced pre-accept tool to do automated measurement. Pre-accept uses a list of 260 possible words that have been manually assembled beforehand and simply search for them in entire HTML structure, which might decrease the accuracy and hard to escape. Plus, it doesn't consider rejection. Throughout the start, I'm going to introduce the automated tool we implemented to analyze cookie landscape from different perspectives. But first, let's talk about the methodology we use for collecting the data. Initially, for each trial, it opens the domain from the target list, then it starts to collect the cookies, and then it starts to attempt to detect the banner, and then interact with the banner. And during this, during time, it keeps collecting cookies for a fixed amount of time. And this loop will be repeated for all users in the target list and then the stateless one. The whole process can be divided in two separate parts. First part is related to data collection, and the second part is responsible to detect and interact with the banners on the website. The left part is already implemented in the open source privacy measurement framework named OpenWPM, and for the right side, using Selenium browser automation, we implemented tool which can detect and interact with the banners, and we named it Ban and Click. And so by integrating these two parts, we have the desired system to collect the data and complete it automatically. What we expect from Ban and Click? First, it needs to detect the banner in a given website. After detection, it should be able to interact with the banners and click on the option we want. For example, if you want to investigate the behavior of the website after opting out, it should be able to click on the reject button. Of course, if such an option is available on that particular banner. Now let's see how Ban and Click works. For answering to detect a banner, actually we need to answer. We need to know how is the structure of the HTML page. Typically, banners are a separate shot of the body type, which are included with the cookies-related text. And the banner detection algorithm needs to find three specific nodes sequentially. First is the end node, which is a node with the cookies-related words like cookie, accept, privacy policy, and these kind of things. And second is the first node, which is a node with the CSS fixed position fixed property. And using CSS fixed position property is a good heuristic because, as we know, most of the banner are fixed and we don't. And after finding these two nodes, we traverse the path from the first node to end node to find the optimal node. Optimal node is the minimal size node in the path that encompasses all the visible HTML elements in the path. So that's it. Now we have the optimal node, which is the root and the main representative of the banner. And we run this detection process for triangle top 10, triangle top 1000, and check the screenshot manually, and we saw it's worked with 99% accuracy. Now we have the banner doom, so we can interact with it more accurately. To do this, we just need to find a button that leads to the interaction mode we want. For example, for accept banner click looks for words inside the banner that semantically are related to accept, like accept, agree, confirm, and these kind of things. And same things happen for reject, except for reject. It checks for possible reject button by clicking on the setting option of the banner. This is because it thought some banners show the reject option in the setting of the banner. We collect these three word sets for top 13 languages that are the most occurring ones in top 10,000 domains. We run the measurement on 8 vantage points spreading across 6 continents. 2 of them are in EU countries and 1 in California, so we can see the possible effect of GDPR and CCPA. As for the target list, we use Tranco top 10,000 domains. In total, we are able to detect banner in around 47% of the website in EU countries and around 13 in non-EU countries. This definitely shows that GDPR has effect on the behavior of the website on showing banners. Moreover, looking at the blue part of the line, we can see that near half of the website in all vantage points don't have any easy to opt out option, which might be interpreted as not completely complying with GDPR. Next plot shows the box plot for number of cookies for different interaction modes in Germany. You can see how interacting with banner can substantially impact cookie distribution. For example, after accepting a banner, the number of first-party cookies increased by more than 1 time, and the number of third-party increased by 5.5 times on average. As for tracking cookies, the average increased from 0 to 7, which shows a substantial impact. Furthermore, we see that the number of tracking cookies is near 0 when banner is not accepted, which indicates the effectiveness of GDPR to reduce unwanted tracking. As for reject, we can see for both first-party and third-party cookies, the average increase by 1. This might be attributed to cookies the cookies which are set to save the state of the cookie banner. And for tracking, we see no differences between cookie before and after reject, which is in compliance with GDPR. This plot depicts ECDF graph for the fraction of websites with respect to the number of cookies they set. It shows that websites set less cookies in EU countries when compared with non-EU countries. For example, we can see 80% of the websites set fewer than 11 in EU, whereas 70 cookies for non-EU. And regarding tracking cookies, we see that 60% of websites set less than 1, while this number is around 6 in non-EU. And this figure shows the difference between the average number of cookies when visiting websites with the different user agent in no interacting mode for 3 countries, Germany, Brazil, and Belgium. So the majority of websites behave the same and set the same number of cookies. It's obvious the user agent will impact the number of cookies. Some websites set more cookies on desktop and some set more on mobile. We detect a similar number of banner on website when visited from desktop and mobile. Furthermore, we explore the prevalence of content management platforms or CMPs on the web. CMPs are platforms that offer cookie consent handling as a service. That is, website can include a ready-to-use yet configurable banner instead of developing their own cookie banner solution. In this figure, we can see the distribution of top 6 CMPs over the top Franco list. As it shows, these top 6 CMPs attain around 70 of the whole market share. Based on the figure, in average, more than 10% of websites use CMPs. And interestingly, we can see that top 50 websites don't use CMPs to implement the banner. It might be because of the fact that the very top websites prefer to have a complete control over their clients' data and how they want to handle it. Before conclusion, I would like to talk a bit of my personal insight over web cookies landscape, in particular how the user functions are collected. It seems that banners are just merely a straight way of complying with laws, which are kind of ad hocly developed by publisher to avoid fines. However, from an engineering perspective, they may not be the most optimal and user-friendly solution. They are typically considered as annoying, which needs too much effort to comprehend and interact properly. As you can see, there are many variations of this in the web. Moreover, as the previous research have shown, many of banners use dark patterns to coerce users to click on the accept. Not to mention cookie walls that ask for monthly ad-free subscription as an alternative to not accept it. These all in all make the user decision completely biased and subjective, which are based on time and mood and not the overall interest. With that said, as a rough prediction, I would say the cookie banners, as they are now, have no future in the internet utopia. Probably, if big companies finally agree on, we end up to a decent solution which are supported in the application layer. Currently, there are some progress in this area. For example, Google's privacy sandbox aims to replace third-party cookies with a more privacy-conscious approach, allowing users to manage their interests and grouping them into cohorts based on the similar browsing patterns. And personally, as a user, as an internet user, for me, the best solution, the best possible solution is one which I would be able to opt out by one simple click for the entire browsing experience. To summarize, in this paper, we investigate, in fact, the different factors on web cookies like like the location of the user and their interaction with the banners. We also introduce our tools management to run the measurement in an automated way. And for more details regarding banner click and analysis, please check out our paper. There you can find more about impact of different factors on web cookies like CCPA, landing versus inner pages, and also consistency analysis. Finally, you can find the data and analysis script which are available in banner click Git repository. Thank you.
Thanks for joining us. Regrettably, the audio did not work very well during your presentation. So we don't have anyone in the queue for questions or comments right now. If there is someone with a comment, you're welcome to join right now. But otherwise, I think we're going to go on. And we just couldn't do anything about getting the audio to be better. And we weren't able to isolate why. Thanks for joining us. Folks, you can contact him directly by email or use the chat.
Thank you.
Rania, we have her queued up to share her slides, which I just did right now. And Rania, you should have local control of the slide deck once that's done. And you're welcome to turn on your video. Actually, it's nice for the participants here to be able to see you while you're talking, if you don't mind. There we go.
Awesome. All right. Is audio working fine?
Can you just say something again?
Can you hear me all right?
Yep. Yeah, it sounds good. All right. You ready to go, Rania? You got up to 15 minutes.
All right. Perfect. Thank you. Well, thank you for having me. And today I will be presenting our paper on user awareness and behaviors concerning encrypted DNS settings in web browsers. And this work has been published at Usenix Security 2023. So the encrypted DNS ecosystem is increasingly becoming a place where various internet stakeholders try to vie for control through technical protocol design. And really, these design choices affect market consolidation and power, corporate visibility into and control over user data, and user privacy on the internet. And at the end of the day, humans are impacted the most by these decisions, which is really why it's essential to study their awareness and knowledge of these settings. Recently, many major browsers and operating system vendors have deployed encrypted DNS functionality, and particular configurations of these settings are often enabled by default. So in many cases, default encrypted DNS settings have implications for performance and privacy. An example of this is that until recently, Firefox sent all the users' DNS queries to Cloudflare through their default DNS setting. And really, this creates privacy vulnerabilities since one resolver sits on heaps of user data. And this recent centralization really just causes significant issues of power dynamics, which is what we sought to better understand. So our study confirmed that most users are unaware of these new technologies and the subsequent implications. So some background is that the domain name system, also known as DNS, maps human readable names to IP addresses. And historically, these DNS queries are conventionally unencrypted, which really just leaves queries and responses vulnerable to eavesdropping and manipulation. However, with encrypted DNS, protocols such as DNS over TLS, known as DOT, and DNS over HTTPS, known as DOH, as many know, have emerged to encrypt these queries so that they're no longer vulnerable to third parties. So in our study, we studied encrypted DNS settings in Brave, Chrome, Edge, Firefox, Opera, and the Android mobile operating system. So say, for instance, after hearing about what encrypted DNS is, say that Sally wants to try enabling encrypted DNS after just learning more about it. This is what she would do in her Chrome interface. First, she'd navigate to the Settings tab. Then she'd click on Privacy and Security. Next, she'd scroll down and click on the Security tab. Then she'd find the Use Secure DNS setting, which is how they enable encrypted DNS, and she could toggle back and forth to enable it or to disable it. Then say she wants to enter a custom resolver, like she wants to use Google's resolver. Say she types in google.com as a custom resolver. Here we see that she gets an error because it's incorrectly formatted. Then she enters it in the correct format, which is dns.google/DNS query, and then it has full functionality, the resolver. So as this demonstrates, the settings page is not easily accessible, and very little explanation about the setting and resolvers are actually given, which significantly affects the user's understanding of the resolvers and their interaction with it and the overall encrypted DNS page. So Brave, Chrome, and Edge all operate similarly in that they refer to encrypted DNS as secure DNS. If a user makes no changes, the browser uses the user's default DNS resolver, and it falls back to sending unencrypted DNS queries if the encrypted DNS resolver is unavailable. On the other hand, Firefox and Opera refer to encrypted DNS as DNS over HTTPS, and Firefox's default behavior is to use encrypted DNS with Cloudflare as a default resolver. And interestingly, Opera disables encrypted DNS by default, but when encrypted DNS is enabled, Opera uses Cloudflare as their default resolver. And another interesting point about Opera is that only Opera explicitly mentions that DOH uses third-party services. Mozilla operates a trusted recursive resolver program, and that they ensure that DOH providers recommended by Firefox best protect privacy by not over-collecting and sharing data. As also demonstrated here with the dropdowns that all the browsers provide, some of the resolvers shown in these interfaces offer additional features such as blocking malware or adult content. So the research questions that we explored are users aware of encrypted DNS settings in browsers and devices? What encrypted DNS settings do users have enabled? Once shown encrypted DNS settings for different browsers, which settings do users select, and when the technical aspects of these systems are explained to users and they really just have a broader understanding of how encrypted DNS works and what the DNS is, how do their choices of these settings change? So our study consisted of a two-part survey, and we recruited participants via Prolific, and they were compensated for their time. In the initial screening survey, we asked 800 participants about their use of different popular web browsers, and based on their responses to these questions, we assigned participants to subgroups determined by the browsers that they reported using at least once a week. After assigning participants to subgroup according to browser, we invited up to 50 participants from each group to participate in a second, longer survey, which was our main survey. So our main survey had 184 participants, and the structure of the main survey was as follows. So first, we asked participants if they had heard of the DNS prior to the study and if they knew what DNS did, really just trying to gauge their understanding of it prior to the survey. Next, we randomly assigned participants to anonymized versions of actual DNS settings that can be found in browsers. But rather than simply showing them a screenshot of their assigned interface or multiple choice questions that kind of resembled an interface, we embedded interactive versions of the browsers directly into the survey so that participants could really interact with them, and it would simulate what their experience in a browser would be like. Next, we asked participants questions about their rationale for choosing different options, and really just wanted to understand why they chose the settings that they did. And we showed participants an interactive version of the private DNS setting on Android as well, and once again asked them about the settings that they would choose. Here, N represents the number of participants that were assigned to each interface. Next, we described the DNS, and we checked participants' understanding through a multiple choice question about the basic functionality of DNS, and really just explained in more detail how the specific settings work. And given this additional information, we asked their thoughts on the setting. After that, we showed participants the interactive encrypted DNS settings screen that they saw earlier in the survey and asked them once again to decide what options they would choose and why. And the reason that we did this was that it allowed us to really understand how respondents changed their settings after gaining a high-level understanding of what encrypted DNS does and the benefits that it provides. Finally, we asked participants to report on the current DOH settings in a browser that they regularly use. So we really just asked about their experience with navigating these settings and enabling or disabling them. And the browser that we assigned participants to look at depended on their responses to the screening survey. So if for some reason a participant did not have access to the browser subgroup they were assigned to from the screening survey, we reassigned the participant to another browser that they did have access to. Once again, and over here, relates the number of participants assigned to each browser. The first question that we look at in our results is, are users aware of encrypted DNS settings? Here we find that 73% of all participants reported having heard of DNS prior to the survey. Of the participants who reported having heard of DNS, 59.9% had heard of encrypted DNS. And when participants who claimed to know the purpose of DNS were asked to describe it in their own words, fewer than half mentioned the DNS as being responsible for translating domain names to IP addresses. And we find this interesting because participants had various misconceptions of its purpose, including that it identifies computers on a network or connects devices to the internet, which we all know is not really what the DNS's function is. Next, we find that regarding stakeholders in the encrypted DNS ecosystem, most participants had heard of Google and Comcast, but were less familiar with Cloudflare, NextDNS, and Quad9. So what encrypted DNS settings do users have enabled? We find that 79.4% of participants had the default settings enabled in their browsers, which typically meant that participants' browsers were opportunistically encrypting their DNS queries. We also found that no participants reported correctly configuring a custom DNS resolver in their browser. Participants entered queries such as McAfee or Google.com or 1.1.1, and they weren't correctly formatted as when needed for their queries to actually be encrypted. So when shown encrypted DNS settings for different browsers, which settings do users select? When shown the anonymized browser interfaces for encrypted DNS, 71.7% of participants continued to use the default settings shown to them. And this finding really just illustrates the importance of how browsers and mobile service providers configure their defaults. When participants did enable encrypted DNS but did not go with the default setting, they were much more likely to choose a resolver that was listed in the setting rather than just specifying a custom resolver. And as earlier explained, we saw the issues with the custom resolvers. So in choosing a resolver that was listed in the settings page, Cloudflare was by far the most popular. We also found a strong connection between the name of the setting and the perceived impact. And as discussed earlier, the two names of settings in browsers are Secure DNS and DNS over HTTPS. With Secure DNS, we found that participants associate Secure DNS with safety and security. So secure was in the name. They thought that the setting had something to do with security. Here, one participant said, the wording makes it sound like enabling DNS would make my browser more secure. Another said, I don't know a lot about it, but it seems like an extra step of protection, really just associating the setting with security, and that had a major factor into how they either enabled or disabled encrypted DNS. Next, for the DNS over HTTPS setting, we found that interfaces that label the setting with the technical name DNS over HTTPS caused additional confusion in some participants because instead of interpreting the name as meaning DNS using the HTTPS protocol, they interpreted DOH as meaning using DNS instead of HTTPS. And of the participants who saw the Firefox or Opera interfaces that label the setting in this way, 10.6% mentioned an incorrect interpretation of the setting name as part of their reason for choosing the setting option that they did, which we found was quite significant. Here, one participant said, I have no earthly idea what DNS is, while I'll at least have a passing familiarity with HTTPS. And another said, from the little I know, I believe that HTTPS is more secure than DNS, really just highlighting this name confusion. And really the impact of all of this is that it emphasizes the issues of technical jargon and the necessity of explaining concepts to users. Is audio working fine? All right, thank you, apologies. Okay. Next, I found that when the technical, again, aspects of these systems are explained to users, how do their choices of settings change? So after being provided a description of what the DNS is used for and what encrypted DNS does, 37.7% of participants chose to modify their settings in some way. And 30 participants reversed their choice, with an equal number choosing to disable the setting that they had previously enabled and enabling the setting that they had previously disabled, which was quite a significant number and really just showed how participants changed their interaction after receiving greater knowledge of what encrypted DNS is and how the whole process functions as a whole. So based off of our findings, we make the following recommendations. First, we recommend to provide a basic primer on DNS function and the privacy risks, really just to explain DNS function, privacy risks, and the trade-offs associated with each setting. Next, our results indicated that while participants understood the setting after it was described to them, they still struggled to understand the differences between the recursive resolvers. So we recommend providing privacy policies for these resolvers, really to just lead to more informed choices and to help users understand the differences between the recursive resolvers. Be thoughtful of the technical protocol terminology. Again, this was really highlighted with the DNS over HTTPS name confusion that we found when participants didn't understand the setting correctly, and that really impacted the ways that they interacted with it. And finally, provide users with the necessary format to select a custom resolver, adding instructions, guidelines, and warnings for more clarity. So in summary, we study user understanding and awareness of encrypted DNS settings in 4 browsers and the Android operating system. And we suggest practical recommendations for designers and policymakers based off of our results. We indicate that work is needed in several areas, including to improve user awareness about the privacy implications of DNS, to provide users with information to better understand the implications of how encrypted DNS is configured, and to design setting interfaces that make these options intuitive for users to customize. Thank you for your time, and I'm open to any questions.
Thanks a lot, Rania. We're running a little short on time for the meeting, so we've got 3 people in the queue, and we'll take Ted Hardy first.
Ted Hardy speaking. Thank you very much for the work and for bringing it here. Very interesting indeed. 2 quick questions. One, if I understand your methodology correctly, you did random assignments to the online browsers that enabled the interactivity. May I ask why you did that rather than by picking the people who had self-selected particular browsers? Because there is at least an impressionistic sort of anecdotal association between people who have already selected non-default browsers and security consciousness, and it would have been perhaps a different question had you done it that way. And I kind of wonder why you had made that choice.
Sure, definitely. So I completely understand that. What we did in our methodology was when we showed anonymized browser interfaces, that's when we randomly assigned users to them. And that was really so that we could get an equal amount of people that were looking at each of the interfaces, rather than we found that many people by default use, say, Chrome the most. And we found that Brave and Opera, many participants weren't as familiar with those interfaces. So really by just randomizing participant assignment to these browsers, we could have a greater and more equal amount of people that were looking at each one, kind of just to spread it out evenly. And the reason that it was anonymized was so that participants did not know at all which browser they were actually looking at, whether it was a browser that they were familiar with or it was a browser that they had never looked at before.
Thank you very much for that explanation. The second question, in your discussion of future work or potential adjustments for this, were there particular pieces of data that you felt sharing with the users gave them the best chance of deciding whether to change the settings or not? Or were you using a script so that every time you were presenting it in exactly the same way?
We were using a script to show, like, every participant received the same explanation. I think that would be a very interesting other part to the survey to kind of show different explanations and see how participants' choices of settings changes based off of that. But what we did find, we asked participants what they would like to see or what they would like to know more about encrypted DNS when making their choices. And we found that a lot of participants wanted just more explanations, that there wasn't as much technical jargon, and that it was easier to understand if they didn't have a computer science or networking background. And they wanted pros and cons listed for each resolver setting and just the encrypted DNS setting as a whole.
Thank you very much.
Thank you.
Ben Schwartz, thanks for doing this very deep analysis. I really think this is fantastic, and I hope the browser vendors are paying close attention. I do believe that the Chromium interface does provide a link to the privacy policies of all of the resolvers in the dropdown, and probably some of the other browsers do as well. So I think that's a great recommendation, but it is partly already being followed. If you're interested in future work in this area, I would encourage you to look in different markets where the role and purpose of encrypted DNS may feel a little different. For example, I suspect that if you ran a survey like this in Indonesia, you would get very different kinds of answers than you get from one run in the US. Thank you.
Definitely, thank you. I think that would be an appropriate next step.
Wes Herdeker, USC ISI, and the ICANN board, speaking for neither of them but myself. Excellent work. Thank you very much. We need more studies like this to figure out, how well user understands, security settings in particular. One of my wondering while I was listening to you is, in the education section, did you talk to them about the differences in potentially giving their data to one large company that, you know, is a DNS provider versus giving it to their ISP, which may be a different large company, you know, and providing them different services? I could even see this leading to different choices depending whether it was a mobile device they're wandering around with or whether they were at home and maybe trusted their ISP or something.
Yeah, definitely. We actually did in our survey, and something interesting was we asked participants like if they would rather their data be given to a smaller company or to their ISP. And if you are more interested in this, I do recommend reading our paper. We have a section where we analyze how users decide whether they would where they want to share their data and whether they want a larger company or a smaller company to see it. So that is further in our paper.
All right, thanks so much for joining us, Rania. That was interesting. We're going to have Rob Beverly up next. I'm going to share his slides right now. We had about 28 minutes left, so the final two presenters, if you can, we're going to have 15 minutes for each of you with the questions and comments within those 15 minutes. Rob, you should have control now, and your first slide's up.
All right, great. Thanks, Dave. Can everyone hear me? Hi, everyone. My name's Rob Beverly. Thank you for having me. This is work done primarily with one of my former students, Eric Rye, who's now at University of Maryland. And I'm gonna cheat a little bit here and tell you about two pieces of work. One paper that appeared at IMC and one that appeared at Security and Privacy, because they both kind of rely on the same trick. And so I'm subtitling this, what we did with millions of EUI64 IPv6 CPE addresses. So let me tell you what that means. So this comes from sort of a long trajectory of work we've been engaged in with doing active IPv6 measurement at internet scale. Some of this, dating back several years, even work that I did with Dave and others. And what we've been doing is uncovering some of the behavior of IPv6 deployed in the wild. So things like how IPv6 addressing is done, how IPv6 allocations are done, and even some interesting things like prefix rotation that I will tell you about in a moment here. The end result of this, and sort of the punchline that folks may or may not be surprised by at this point, is that we discover, order of hundreds of millions of CPE, customer premise equipment, that use this legacy form of IPv6 addressing. I'll tell you all about that. And then in this talk, I really want to talk about the sort of implications. And again, the two implications here are prefix tracking and street level geolocation via IPv6. And then I'm also going to say a few words about some remediation efforts because we've made some cool progress in that area. So just so everyone's sort of on the same page, and this is a bit of a simplification for those of you who are experts in V6, but the mental model I think that's useful to have is to remember that at least for residential deployments, as opposed to the typical IPv4 residential deployment, in V6, there's a subnet between the provider's router and the CPE, the home router in the house. And then there's a separate distinct subnet that's behind that CPE router on the other side. This is something we've been calling the periphery for a while. One of the interesting measurement implications here is that we don't necessarily require a responsive target within the customer subnet to discover something about the CPE router. We can send a probe into the customer subnet, which will elicit a response from the CPE router itself in many cases. This allows us to do things like binding the customer subnet to a particular CPE device that's discovered. And so we've been able to do some cool stuff with this. Down in the lower left here are some visualizations of how different providers are allocating subnets to customers. So here's examples of like a /56. This is just a graphical way of looking at the 7th and 8th byte of the prefix that's allocated. And you can see very distinct patterns for distinct providers. So that's all background. One of the things that I'm sure, again, folks in this room are very cognizant of is that RFCs have a long deployed lifetime. One of the questions you might ask is, when we do these IPv6 measurement studies at scale, what are we finding in terms of the responsive addresses from the CPE? And the answer is there's all kinds of things you might expect: static, DHCPv6, of course, privacy extensions, and there's lots of RFCs for that. And in addition, there's this legacy mode of addressing. Again, a bit of simplification, and there's a bunch of additional RFCs for more information, but the lower 64 bits can be formed deterministically from the MAC address of the actual interface. And there's RFCs on this. This has been well known for a very long time, and there's even more modern RFCs that talk about the privacy implications of this. And so, you might ask, well, this has been known for more than a decade, and so what's the status of things? And the status of things, the punchline here is that yes, all modern operating systems use IPv6 privacy extensions, but there's, again, as I said at the beginning, order millions of CPE home router type things that are still using EUI64. So there's two pieces of work that we've written to exploit this, in essence, these persistent identifiers. So the first one that I wanted to tell you about that we discovered is IPv6 prefix rotation. This is something that surprised us initially. The basic idea here is we know, for instance, that the host might be implementing privacy extensions, and the lower order 64 bits of the host may be changing all the time. In addition, however, providers are actually rotating within a particular pool of addresses the assigned subnets, both the point-to-point subnet and the host subnet. So these things can change over time. They can change on timescales of an hour. They can change on timescales of a day. It just depends. And so one of the things that we did in this IMC piece of work from a year or two ago was to try to get a handle on whether we could attack this by exploiting these EUI64 addresses. And again, the high order bit here is that in these prefix rotating providers, of which there's hundreds of these across the world, we find about 9 million CPE devices using EUI64 addresses. So what does that allow us to do? So this allows us to actually reduce our search space so that we can try to actually track individual nodes that have both their upper bits, their prefix spinning, as well as their lower bits spinning. So the idea here, and this is sort of a time lapse of some of our imagined adversary, and we play the role of the adversary here, where we're sending probes into the network, and we may have misses, but when we have a hit, for instance, we're going to see this. We're going to not necessarily see the end host, but we're going to see this CPE address, right? And as this goes on over time, the thing that you're going to note, sorry, let me just move this forward a few slides. The thing you'll note here is that, yes, while the prefixes are spinning and it looks like the addresses are quite random for the end hosts, indeed for the CPE, because they're using EUI64 for the lower order bits, we can again do this correlation exercise. This allows us to essentially track some of these devices. So in this particular piece of work, we showed how we could, at internet scale, do things like exploiting these to track users across both prefix and their host changes. We did a case study demonstrating 60 to 90% accuracy being this envisioned adversary. And we show that this extends across order of hundreds of providers. So the next piece of work that's directly related to this is the most recent piece of work. This is the IPv-CU work. This appeared at IEEE Security and Privacy quite recently. And the idea here, again, was to take these EUI64, but now, in essence, to do a correlation, a large-scale data fusion with Wi-Fi geolocation databases. And the punchline here is that there's millions of residential homes that are exposing their exact physical street-level location via IPv6. So let me tell you how this works and give you a bit of intuition. So I've already demonstrated, hopefully, that one, remotely, without any privileged access, can obtain just by sending sending a bunch of probes into the network and reducing your search space, you can obtain both the WAN side MAC address of the CPE, and it turns out that many of these home routers also have Wi-Fi. They're an all-in-one device. And so what we do then is to say, okay, can we do a prediction that predicts the offset between the WAN MAC address and the wireless MAC address, right? Because often these are system on a chip and they come from the same OUI. So that's the intuition here. If that's possible that we can predict this offset, and in this example, you'll see, for instance, that the WAN MAC address and the BSIDs for the Wi-Fi all come from the same OUI. If we can predict that offset, sometimes it's as simple as, you know, +1, -1, then we could, in theory, query war driving databases to get the exact geolocation. And this is what we did. I'll just point out, in the interest of time, you know, please read the paper for the details. This is non-trivial because we have missing data points, and often it's the case that it's not so simple as being just the MAC address is, you know, +1 or -1 from the WAN address. So here's an example where, and this, we actually purchased devices. Some of these all-in-one home routers, we purchased them to get ground truth to test our algorithms. And it's a statistical-based algorithm, and there's a bunch of details in the paper. But here's an example where naively, you know, this MAC address of this WAN address of this one all-in-one router on the right here is one off from the MAC address of this center all-in-one home router. But however, these are two different devices. And in this piece of ground truth, this is a real example. The true offset between the same device's WAN and the same device's Wi-Fi was either +5 or +6, again, depending on whether it's the 2.4 or the 5 gigahertz that we actually discover in the Wi-Fi driving database. There's a ton of limitations here, right? Some CPE, of course, don't use EUI64. Sometimes they don't respond to our probes. Of course, you know, the BSIDs that are in the war driving databases may not be there, so on and so forth. But what were we able to actually do? So by doing this large-scale data fusion and combining WAN MAC addresses that are discovered via V6 and via this sort of, you know, abstraction layer violation, where these layer 2 things are percolating up into layer 3, by doing this data fusion with BSIDs and with our offset algorithm, we geolocated 12 million unique devices out of 60 million in 147 countries in over 1,000 unique OUIs. There's, again, many more details in the paper. And you might say, well, and this is, you know, very, very much directed at sort of an IETF audience, well, you know, let's just not use EUI64, and that's totally true. But one of the things we also show in this paper is geolocation by association. And so even the non-EUI64 devices are vulnerable to geolocation because the other EUI64 devices are hooked up to the same ISP router, which allows us, just because of the physical medium constraints, to do geolocation of non-EUI64 devices. And there's a bunch of details about that in the paper. So the cool part about this, we did We did engage with a large national scale United States residential service provider, both for validation of our technique, but then they subsequently did remediation. So they actually changed the behavior of their entire network to prevent this. We also talked to multiple vendors of CPE that were doing this. We had mixed results. Some vendors actually told us we were wrong, that they weren't doing EUI64 when we could absolutely tell them that they were, and they just refused to believe us. Fritz OS is one example of a provider that did actually change their software stack to remediate this. With that, I think I've blown through the presentation, and I definitely invite you to check out the papers for more details, and I am happy to take any questions.
All right, I appreciate it, Rob. Bob Hinden's up first, and then we have Rui in there, and might have time for one more, depending on how long these guys take.
Hi, Bob Hinden. So you left out something important. So the IETF has deprecated the use of EUI64. It's not just not recommended, it's just, you know, we've done a lot of, we realized this was a problem years ago. It's been deprecated. And most, I think the vast majority of end systems, phones, Macs, PCs, use the random interface IDs. They don't do this anymore. So you didn't make that very clear. It's not like there's a big project here for the IETF left to do. I certainly agree that the CPE, you know, the ISP provided devices need to fix this. That I was not aware that it was this bad, but that work you're doing, I think, is very good. But for the IETF, I mean, we understand this problem, and I think we fixed it some years ago now, so that shouldn't be an issue going forward.
I want to say maybe people are in the room or watching the talk. You know, it's not that the IETF has to do some standards work, but we can still help, I think.
Yeah, thanks for the comment. Maybe I didn't make that clear enough. I mean, this has absolutely been known as a problem for a very long time. I think that the one point I might make, however, is, you know, these types of devices, they don't really get updated frequently. Like, when was the last time that, you know, my parents updated the firmware on their home router, right? So there's a really long tail here. And I just, you know, I think the point of this work was to, you know, sort of illuminate, and part of my point here was to illuminate the extent of the problem. I mean, again, we're talking hundreds and hundreds of millions of these things are in the wild, but thank you.
Hi, Rupal. This is a great presentation, and I was wondering how you were able to gauge the accuracy of your results, especially when you're talking about street level.
Great question. There's there's a ton of sort of academic level details and rigor in the paper. The short answer is we crowdsourced first with friends and family for a very small data set. But then what we did is we engaged with this large US national secure service provider, and we actually got ground truth from them and did our validation there. So you can check out the paper. Obviously, we make mistakes, but you know, the accuracy is quite high for that case.
Hi, Tim Chang. So yeah, what Bob said, it's not actually deprecated. RFC 8064 says hosts should not use EUI 64s and should use, I think, 7217, the per prefix identifiers generated per prefix. So that would also prevent the issue you saw with stability across when the home network is renumbered, because they get a different identifier because it's a different prefix. So nowhere does it say must not. That's part of the issue. The other is vendors just don't follow standards a lot as well.
Noted. Thank you.
All right. Thanks a lot, Rob. A lot of interest in it. Follow up with Rob outside of the meeting if you can. We have Lai queued up, and I'm going to share your slides, grant your slides right now. And as soon as you see that first slide up, you're ready to go. We've got a little over 10 minutes. Can't hear you, Lai, right?
Hear me now?
Not getting your audio.
How about now?
Yep, there you go.
Okay, great. I had to press unmute, it turns out.
Okay.
So hello, thank you for having me. Thank you for sticking around for the last spot. My name is Lai Olson. I'm representing Measurement Lab. I'm the lead data scientist for the project. We are a fiscally sponsored project of Code for Science and Society. If you're not familiar already, Measurement Lab's mission is to measure the internet, save the data, and make it universally accessible and useful. This is something that we've been trying to do since 2008, and we consider this a group effort alongside all of you in the room, as well as many others, and I'll talk a bit more about that. Really, my goal today is to just open up the conversation around how MAPRG specifically, but as well as the IETF and MLab could be more complementary and work together, collaborate more. I think there's a lot of opportunities for scaling each other's work. MLab was created in an effort to support internet measurement at scale. And so I think it would be interesting to think about how to scale some of even the ideas that we heard today. So just talking through those collaboration points, or to do that, I'll set the stage by talking through just what MLab was created to do and how we're doing that today. And then again, talk more about what we could see perhaps in the future. So why was MLab created? As I mentioned, we were created in 2008 to address sort of 4 primary challenges that were seen as barriers to internet research at the time. Please pretend this says 1, 2, 3, so it seems like I can count. But the first one, either way, is thinking about, or at the time we were thinking about how to measure the internet at scale. So I think this is still often the case, but definitely at the time there were many instances of someone writing an experiment or a tool for an experiment, or collecting interesting data, or coming up with a new metric that people wanted to standardize, but it was written for a paper and then never went anywhere after that. No one was able to collect that data anymore until 5 years later when someone discovered it, and it went through sort of the same cycle. So there was this recognition that internet measurement at scale meant that there had to be a sort of infrastructure and organization to keep that measurement going beyond the life cycle of an academic paper. There's also the challenge of just sharing data sets, large data sets at scale as well. So this, again, in 2008, of course, this has become a lot easier as data sets have gotten bigger and it's become more common to share them openly. But at the time, it was a challenge. And then there was also this consideration of what it meant, or how we could measure the internet, or the so-called real internet. So of course, there's a lot of interesting work done with test beds and sort of localized and controlled measurement in a lab environment. But there was this desire and notion of measuring where real traffic was being sent and being able to collect metrics in that environment. And then the third one, which is, and again, sorry, it says 4, but the third one was thinking about, all of this research was being done sort of in an effort to improve the internet as a whole, but it turns out that needs a lot more than just the internet network researchers to promote those ideas. And so there was this observation that bridging the gap between industry and academic research was a need, but also bridging the gap between industry and policymakers, and having there be a better, more shared understanding about what the needs were for the internet and how policy could play a role in that, how research could play a role in that. And the hope was that if there was open data, then the open data could facilitate a conversation such that we were all looking at the same numbers and looking at the same sort of understanding of how the internet was evolving. So those were the lofty goals that Measurement Lab was founded to create. And so now I'll just talk a bit through about what we're doing to address those challenges, what we've, I think, done a good job at, and what we still are actively seeking solutions for and collaborations with. So the first one is that we now run a platform and an infrastructure. I'll talk more about that. And we also collect a ton of data and publish it for open access. And then through that publishing, or through that collection and publication, we're able to then support researchers, policymakers, and members of industry by using it and helping it inform their work. So the platform is the sort of nuts and bolts of it all. So since 2008, we've grown a platform of 750 sites around the world that each have servers that host our measurement services or experiments. These are placed in interconnection points and as of last year in cloud networks as well. Asterisk there is right now it's only Google Cloud, but we are actively seeking partners to be able to branch out into other cloud networks. So if that's something that you are interested in or know people who would be interested in, I'd love to talk. But in any case, right now we are in 750 plus locations globally. And on those servers, we host what we call measurement services, which are essentially the server side of experiments, such that when a client runs or clients run the test, when an application runs the client side of the test, then they test against an MLab server. And that's chosen based on geographical proximity. So if I'm in New York, I can test against a server in New York and so on. And so right now we host 4 measurement services. And every time anyone runs a test, the results of that test are archived publicly and then pushed into Google's BigQuery tools such that they can be used easily. And as mentioned before, one of those tests is reverse traceroute. We have a test called DASH and then also WIHI and NDT, which stands for Network Diagnostic Tool. I'll talk more about NDT because it has our greatest data volume. So since 2008, we've been able to collect over 6 billion rows of NDT data. NDT stands for Network Diagnostic Tool, as I said, and it measures the bulk transport capacity as defined in RFC 3148 of a single stream TCP connection. It is commonly considered a speed test. This is something that we have thought a lot about in terms of the ambiguity of the term speed, but nevertheless, it is often associated with the notion of speed and the measurement of throughput. And we have been able to amass this amount of data because the Google search, largely due to the Google search integration of our open source clients. So when people Google how fast is my internet, they're able to run an MLab NDT test. And so through this, we've been able to amass a really large amount of data, which admittedly can be quite noisy, but there's so much of it that I think there's a lot of interesting questions that can be asked and a lot of research to be done in terms of its potential use cases. Also worth noting that while the majority of results are collected through Google Search's integration, there's also a variety of smaller scale collections. So for example, Airbnb collects or provides NDT as a way for their hosts to tell their guests about the quality of their internet connection when they're booking a stay and want to be able to work from home or from Airbnb. There's also use cases within local communities trying to understand their broadband availability and digital inclusion. So I definitely don't have time to talk through all of the current efforts at the FCC and NTIA to improve broadband availability in the US, but suffice to say, data and mapping are a huge part of that. And so often we'll see people integrate NDT, organizations integrate NDT such that their communities can test their internet and get a more localized representation of how the internet performance is evolving in their areas. So many tests come from these integrations as well. Consumer Reports integrated NDT into a study about broadband pricing as well as performance in the US. I recommend reading that report if you haven't. And I also wanted to mention that for every measurement that is run on the MLab platform, what we call a sidecar service is run, which includes the PCAP data, the TCP info, and running a trace route from the server back to the client. So this means that for every one of those 6 billion tests in the BigQuery database, these sidecar service tests have been run as well. So there's a lot of data there waiting to be analyzed. Also wanted to mention that we have also started hosting third-party data sets, meaning data sets that we have not generated with the MLab platform, but that have been, in the case of Cloudflare, generated with their own infrastructure, and then we publish it for public use. And so this is all these past few examples are all examples of us providing data in the public interest, such that when we're looking at how the internet is evolving and how the internet has changed over time, we can have as many data points as possible. So in my last minutes that I'm already over, I just wanted to talk through some ideas for how we could be hopefully of use to this group, and definitely the reverse. I think the first is just, again, like there's a lot of data there. It would be great to hear your experience using it and the questions that you're asking. So just using MLab data in the research that's being done in this group could be really interesting, I think. Again, 6 billion rows. There's also the opportunity to propose new data for us to collect. So this could look like two different things. You can propose new measurement services, again, those experiments that run on those 750 sites around the world and growing, and be producing data that will then be published publicly. And then also you can, recently, we can also start thinking about what data sets already exist, but maybe have not been published or don't have the infrastructure to be published, that we would also be interested in providing for public interest. And then I think the last one is just giving us feedback. There's a lot of expertise in this room that we would be, we want to be informed by. And I think you just using the data and or thinking about ways that we could improve the platform, different research that's being done that we could benefit from utilizing within the structure of our data or the structure of our measurements, we would benefit from all of that. So mostly this is just a pitch for you all to be aware that MLab exists and for there to be an open dialogue on how we can best support MAPRG and potentially other parts of the IETF. But because we were, as I talked through, really found to support this kind of work at scale, I think there's a hopefully natural synergy in terms of helping scale your work. So I'm happy to answer questions, although I think I might have ran out of time, but my email address is just back here in the first slide, just lai@measurementlab.net. Thank you for having me.
All right, thanks, Lai. We've got two people in the queue, Ali and then Francois. Let's hit them quickly and we'll wrap up.
Thanks very much. This is Ali Rezaki from Nokia. Great presentation. There is environmental impact and sustainability related work starting at the IETF. And for example, one of the topics is carbon intensity across the network and being able to do carbon aware routing, for example. Have you done any related work, or is there any measurements being done or metrics available already? Thank you.
No, the short answer is no, and the slightly longer answer is that that's absolutely something we'd be interested in. I think because we've collected so much NDT data, there's been a lot of emphasis on performance from that perspective, but I think there's a lot more that our platform can do, and we would be really interested in seeing what it would be to measure that.
Mm-hmm. Let's see. Thank you very much.
Thank you.
Good morning, François Nguyen. Can you show the map again?
Yes. There we go.
So it looks like Russia, China don't seem to have many labs.
That's correct. If those are partnerships that you would have access to, we'd love to hear about it. Those have mostly been just due to our own inabilities to find partners.
And where do you store data? Are there any issues with GDPR or things like this? To store the traces, for example.
Yeah, you can look at so when you take a test, users are asked to read our privacy policy and accept that their measurements will be published online. But we are under this is not probably the right terminology, but they're covered by research under GDPR. Or there's more information on our privacy policy.
Thank you.
Thank you.
Thanks so much. Thanks, Lai, for joining us. Thanks, everyone.
Yeah, I would also like to add, please, maybe can you share more information about how to use the data and what kind of data do we have on the mailing list so we can continue the discussion there?
Absolutely. Thank you so much.
Perfect.
And safe travels to you that are traveling. See you in Prague. And watch the mailing list for the invitation to contribute to that meeting.
Yeah, thank you everybody for contributing and Gori for taking notes.